Alrighty. Well, hello everyone. Today we're going to be talking about software supply chain security and some of the work that we've been doing with package registries and making them more transparent. So if you haven't met, my name is Hayden Blauzvern. I'm a tech lead and manager at Google on the open source security team, where I work on software supply chain security and simplifying code signing within open source. It wouldn't be a presentation here if I didn't mention the owl meme. And the reason we talk about this meme, right, is that we care a lot about the end-to-end story here. It's not just recording proofs and verifying them. It's thinking about the full end-to-end story. How does a verifier in this ecosystem ultimately verify the content that goes into the log? And when we talk about package registries, there's a lot of metadata that we're going to be verifying. There's attestations and provenance for how something was built. And as we're going to talk about in a moment, there's a lot of logs that we might be able to add to this ecosystem. There's a lot of places for transparency throughout the software development lifecycle. And so for that, I propose an extension to this meme. If this doesn't make sense to you, I learned recently that a group of owls is called a parliament. What I mean by this is that there's a lot of opportunities for transparency throughout the system, and there will be a step at the end where we want to correlate all of this together and ideally have one tool where users who want to verify their artifacts can simply say, these are the artifacts I care about for an ecosystem, and we can correlate across a number of different logs and verify all of the metadata that we need to do. So as a brief summary of the software development lifecycle, these are typically the 5 steps that we talk about. You have source, you have a build step. You'll then package your artifact. This is where you'll pull in dependencies, which also have a source and a build step. You'll distribute your artifacts, and then ultimately you'll have some end users consuming them. There's a number of entities that we have to trust throughout the SDLC. On one end, we have entities like SourceForges, GitHub, or GitLab. You have builders, and more frequently, CI/CD pipelines like GitHub Actions. Of course, at the packages step, you have dependencies where you also need to trust their SourceForges and builders. The distribution step is where we'll primarily talk about throughout this presentation, which is where we have package registries. These are central sources in an ecosystem, which makes it great to work with them when it comes to improving security of an ecosystem, because these are central sources for distributions. And then typically package registries will also ship package managers for end users to use to install packages. There's a number of different threats that we need to mitigate throughout the SDLC. And as you look at this list, you can think about where transparency makes sense to mitigate some of these threats or add discoverability, or where maybe it doesn't and we have to focus on something else entirely. We're going to primarily focus on package registries, and there's a few threats that I want to mention. One is the risk of stolen or leaked credentials, where a user's credentials are compromised and it allows a malicious actor to upload to the package registry. Another is malicious mirrors, where mirrors serve different content than what's in upstream. And another example is the registry itself may get compromised and end up serving different content than what's expected. So let's start talking about the process of uploading and downloading from a registry and where we can apply transparency. So this is the most simple example to start with. This is the typical process of uploading to a package registry. Some user is going to request an API key. They'll store that API key on a laptop. They'll build locally, and then they'll use that API key to upload. But for one reason or another, this API key might get compromised. Maybe you install something malicious onto your laptop, it gets stolen, maybe you lose track of it, maybe that API key gets uploaded as a build artifact. These are real incidences that have happened. And at this point, now a malicious actor can upload a malicious artifact to the registry. Well, maybe you as a developer choose to switch to using CI, maybe just so you don't have to build on your laptop, or maybe you see it as a more secure environment because it's hosted. Well, it's the same setup here. You're going to have an API key. You'll store this instead as a CI secret, and then that API key will be used to authenticate to the registry. Well, in this case, you still have this long-lived credential, and it can still be compromised, right? We saw in an earlier slide that there were many different threats throughout the SDLC, and for CI workflows, one of them is misconfiguration. This was just one example that I wanted to highlight. There are many, many examples of this, but this was in a case where a popular AI repository, Ultralytics, was compromised through a misconfigured CI environment, and an attacker was able to exfiltrate a PyPI token for the Python package index and upload a crypto miner. So this brings us to one solution to this problem, which is trusted publishing. And the goal is to get rid of these long-lived credentials and move to ephemeral credentials where we don't have to worry about long-lived compromise. And the way that this works, it leverages CI workflows that are able to request identity tokens. So platforms like GitHub through GitHub Actions or GitLab CI also host identity providers. So when workflows run, they can request an identity token. And then this token can be used to authenticate to the registry. So there's an initial onboarding step where a user registers a source repository, or maybe more specifically a CI workflow. And then that token, which will contain the workflow and the source repository information, will be used to authenticate to the registry. This has been implemented in a number of package registries. One of the working groups that I work with published a guide for how this can be implemented. This has been rolled out in NPM most recently, but also the Python package index, PyPI, and Ruby gems. But as I said, misconfigured CI is still very much a real risk here, right? We've moved from long-lived tokens, where if an API key gets stolen, it can repeatedly be used to upload artifacts. But we could still have misconfigured CI that lets an attacker request an identity token, or maybe entirely compromise a source repository and release artifacts through this pipeline. So this is our first example where we can apply transparency. I work on a project called SigStore, which is focused on signature transparency. And what's great about this trusted publishing workflow is it's very seamless to integrate transparency into this pipeline, so we can have discoverability for when artifacts are published. So everything's the same here, except there'll be an additional step where the CI is going to request a code signing certificate for this identity. And the CI pipeline will sign an artifact and then upload this signature to a transparency log. So artifact owners are able to monitor these logs to know when their identity shows up. And if they have any unexpected cases, they know that there was some sort of compromise. And then this provenance will also be uploaded to the artifact registry, so any users can verify this provenance and any inclusion proof for this provenance as well. One of the other things to mention is what this identity actually is. So it's not like an email identity, it's a reference to the build environment where this happened. And what this ends up giving us is a cryptographic link between build and source. When we have one of these code signing certificates, we're able to look at the identity and go all the way back to the source code. So this gives us more auditability into the trusted publishing pipeline. And again, as we think about this end-to-end verification story, we're able to take a proof and take the provenance and go all the way back to source so that we're verifying what we're using was actually what was built from originally. So this is the first step along a process that we'll call transparent releases, where we want to add transparency throughout the SDLC. So what's auditable thus far? Well, the build process with signed provenance. But there's a number of other opportunities to add transparency to the upload and download pipeline for package registries. And there's a number of questions we might want to answer with transparency. So one is the package registry publishing the same package that the maintainer intended? Is this same package being distributed to all callers, or is the package registry serving different packages to different callers? Are mirrors distributing the same packages as upstream? Are there any unexpected versions of my package? Maybe I published v1 and v2, but for some reason the registry is serving v3. Is that transparent? If provenance is present, how do I verify it? What's the expected key or identity that should be used to verify the provenance? And of course, thinking about this full end-to-end story, how do I as a maintainer make sense of all of this information? So binary transparency is very much a catch-all term. So here I'll define this as immutability and auditability for published artifacts. All consumers will receive the same artifacts given an artifact identifier, and we have a globally consistent view. Now, I don't need to talk too much about Go because we heard a lot about this in the previous talk, but Go is a great example of binary transparency with its checksum database that includes this mapping between a package identifier and a digest, which will guarantee that all users are going to download the same artifact given a package identifier, and it will prevent Go's module proxy from being able to tamper with artifacts. So we can generalize this process for any package registry. What's needed is some unique package identifier for an ecosystem. So one example is taking a package name, a version ID, and a file name. But this could be something else. It could be a URL, for example, as long as it's logically immutable. So for one example, in Git, tags are mutable, so those are not great as identifiers, though you could build a system that requires those to be immutable, for example. Each log entry will be a package identifier and its package digest. And what a proof means from the log is that there's a cryptographic commitment that a specific package identifier maps to a digest. So why are checksum databases great fits for registries? Well, one, they're very simple to integrate into the registry and tooling. As we've heard from some of the other talks, it's become a lot easier to operate logs. And so registries can host checksum databases, and whenever an artifact gets uploaded to the registry, they'll record this artifact in the checksum database, and then store an inclusion proof that comes back from the checksum database. And again, this proof can also come with a witness checkpoint. And then tooling will verify these proofs whenever an artifact is fetched. What's great about this process is it's entirely seamless. It's invisible to consumers. The tooling is able to automate this whole process. There's no trust policy beyond what logs and witnesses are trusted by an ecosystem. So this is in contrast to something like provenance, where you need to know some identity or key provided out of band. The other thing that I really, really love about checksum databases is that we can enable them for all packages the minute that a checksum database is rolled out. Again, this is in contrast to something like provenance that requires artifact owners to actively participate, to sign and upload their packages. So we'll always have a long tail of packages that don't have signatures. But for a checksum database, whenever we spin one of these up for a registry, we can backfill it with all artifact digests that are distributed by the package registry, which means the tooling doesn't need any sort of policy to say some subset of packages might not have a proof. No, all packages in an ecosystem will be required to have inclusion proofs. So what are the threats that a checksum database mitigates? Well, one, tampering of any existing versions. This is because you would corrupt the log in doing so. And also, if you were to upload an additional mapping of a digest, an identifier to a different digest, this would be verifiable, and again, would invalidate the claims that the log is making. This also mitigates mirrors acting maliciously because they have to distribute the same proofs as what are distributed in upstream so that we have this globally consistent view. And this also lets us detect whenever any unauthorized packages are published. Now, this requires active participation from artifact owners, but what we heard yesterday from Martin with verifiable indexes, we have a path forward for greatly simplifying monitoring, and I'll demo that in a moment as well. All right, so that answers the first 4 of our questions for transparent releases. So the next one is, how do I verify provenance when it is present? So we said that each log entry is a package identifier and a package digest. Well, what if we also add the trusted publishing identity? And we can also imagine adding in any additional metadata that we might want to make discoverable. But for now, we'll focus on the trusted publishing identity. What this gives us is a way to audit any time publishing identities change. And it is expected that they might, a repository might be renamed, a workflow might be renamed, but we'll now have a history of this. And again, talking about verifiable indexes, we can create an index based on identities, so it's very easy to see where is my identity used, and we can also create indexes based on artifacts, so we can see identities changed over time, and artifact uploaders are able to verify that these changes are expected. So let's put all this together for a real-world example. And this is the proposal for what we'd like to add to the Python ecosystem. PyPI would host a checksum database. And the Python ecosystem already has a way to define package identifiers. So PyPI is able to host source distributions and also something called wheels, which are pre-built artifacts. There are specifications that define unique identifiers for these. So we'll use those for what gets uploaded to the package, to the checksum database. Now, for any ecosystem just starting out, they could also look at the package URL spec. So this is a proposal for how to standardize unique identifiers across ecosystems. Now, some ecosystems already have their own identifiers, like PyPI, but for those that don't, this would be something to look into. Potentially, it would let us build kind of a generic checksum database that would work across different ecosystems, but it's straightforward to build this for each ecosystem that comes along. So we don't necessarily need to standardize across all checksum databases with the URL. Users do need to know which identity. Again, this identity will be present in the checksum database, but they need to know which identity should be used to verify this. So for Python, we'll ship this in a lock file, which also contains all of the dependencies for rebuilding an artifact. On upload, PyPI will log an entry and store this inclusion proof. And then whenever an artifact is requested, PyPI will serve the lock file, the attestation, and this checksum database proof. And then a package manager will be responsible for verifying all the proofs and signatures. So that brings us to our last step, which is what should this all look like end to end? How does a maintainer verify everything that we've seen thus far? And I mentioned this already, but verifiable indexes are a great way to do this. It would let us answer questions like, did I release this version? Did I sign this version? Or what artifacts have been signed with my identity? So monitoring will connect all of this. And what I'd really love to have is one tool that simply connects everything given some artifact identifier. So it would let us verify that our artifact signing identity points to source. It lets us verify that artifacts are in the checksum database and the signing identities in the checksum database. And we haven't really talked much about reproducibility, but if an ecosystem does support reproducibility, you also could use this identity to go back to source and then rebuild from source to verify that that artifact digest is also in the checksum database. All right, so I have a real quick demo just to show this all working together. So what I have running here is a checksum database. This is on GitHub, though this has a few changes that are just local right now. If you're curious about the technical details, this is using Tessera. I'm using the POSIX backend, so we're serving tiles just from a directory. I've got another script that's been running actually for quite some time that's currently backfilling this. I've put some aggressive rate limiting in place just so I don't overwhelm PyPI by trying to download all artifacts very quickly. But you can see this actively populating the local instance of the log. Now, in a real-world deployment, we could imagine that PyPI will just be uploading this. It's not going to have to parse a stream, but you could also imagine that an auditor could rebuild a checksum database based on this stream from a package registry and compare it against the checksum database that PyPI is serving. So I have here running two verifiable indexes. This is based on the code that Martin showed off yesterday. And then we can see here this working. So this is an example of looking up a Sigstr SDK that was written in Python. So you'll just see this running, and then this will dump all examples where this has been found in the log. So here's just one example. This is at index 113, where we have this release with this digest, and we also have an example where this included provenance. So we include the publishing identity. I can scroll all the way up to some examples where we didn't yet have publishing identities or provenance included for these before this was rolled out in PyPI. So you'll see an example here of that. And then we have another verifiable index where I can look up by identity. So this will return a subset of the list. Again, this will return just all places where we have found our identity used. And again, you can imagine this all kind of working together, but this last step, this is just running a tool to verify the provenance, which is also verifying the inclusion proof. You can see here, this is the repository, so this is effectively the identity that's used. And this provenance file also includes an inclusion proof from the SIG-Store signature transparency log. And if we run this, we'll see that it says this has been verified. So again, you can imagine that we could hook all of this together into one tool that makes it very easy for artifact owners to audit everything that they've published and signed. Alrighty, well, that brings us to the end. Thank you all very much. Any questions?
Any questions? No questions. Yeah, one question.
Thank you for the presentation. So you say that somebody could rebuild the same log with the feeds. Would they have to make sure that everything is received in the same order, or is everything ordered on the server side already?
You're right. You'd have to have the same order. So right now, I have not. I've just ordered everything alphabetically as I've been scraping it.
Okay,
so you would need the order. I believe there is a feed that is ordered by upload time as well.
Great. Okay, so that will work.
Yeah.
He kept turning off the microphone yesterday. It was a problem.
All right. Are there any interesting differences between using the checksum database for Go and doing this now in a different context of PyPI? Because I imagine they're slightly different. So did you encounter anything that was surprising or any new insights that you can share doing that sort of integration work?
It's a good question. There's not too many differences. So obviously Go has a different format for what goes into its checksum database, right? That it has both a checksum and of the module and also of the go.mod file. So this is a little different than in Python, where you have different artifacts that are being uploaded. So I would say that's one difference. And again, if we think about the end-to-end verification story and reproducing everything, that would look a little bit different. I do think this can be mostly standardized across ecosystems, just with each ecosystem making a decision on what exactly gets uploaded to the log. We'd still need monitors that are unique for each ecosystem, though.
Anyone else? Okay, well, let's thank Hayden again.